Hi, this is Jerry Stokely, founder of ReefWorks, and welcome to Process Control Made Easy, stage number 3 control charts. Let's look back and see where we've been. And in stage 1, we calculated the standard deviation, which is really the foundation of overall process control. So if you don't have a good understanding of that, go back, take a look at it, go through the exercises, and make sure that you plant that in your brain. In stage 2, we used Excel to visualize our normal distribution. And in stage 3, we're going to bring it all together and put it into control charts. So really, what is a control chart? Well, a control chart comes from the formative days of statistical process control, or SPC as it's known. And it was originally designed to help operators make adjustments to the process after a signal that the process wasn't centered. It is truly a test for evidence that the process is not under control, and that is the process has moved one way or, or the other way. When used with rules and they're consistently applied, it's way better than pass-fail testing. It'll really improve your quality. Control charts, though, this is a bit of a warning, they're a look-back mechanism. They are not forward-looking. Are they still worth building a control chart? Absolutely, because it is a foundation. If you don't have closed loop control at this point, it will definitely help you with overall quality, and it'll assist in process history. It serves as a training tool for operators so they get a better understanding of variation and how it affects them. So with that, let's jump right in. And let's take a look at a control chart and really how it's built. A control chart is a normal distribution turned on its side, and it looks like a table. Now we've added some colors here. We'll explain that in just a little bit. And they really answer one single question, and that is there any evidence that my process is not where I want it to be? And we do that by looking at probability of a result ending in a ending up in any single category. The question is answered either by taking single or multiple samples, and when you do multiple samples, you average to get the results. So you're working with a double average, the average of averages, and then calculating a range among multiple samples, which in a continuous process is really the way to go. So let's take a look at the standard deviation and the normal curve. We've just thrown in the average, that's the center of the process. We have 1, 2, and 3 standard deviations. You can take a look at our process data, and the normal curve represents the baseline data with the average of 299 and the standard deviation of 69.506. It's important to note the percentages you see in the green, yellow, and red bars. Those correspond to the percent of values, if your process is centered, that you can expect to land in those spots. So plus minus 1 standard deviation is 34.1% on each side, 13.6 between 1 and 2 standard deviations, and 2.1% between 3 standard deviations. Now if you're outside of 3 standard deviations, that's a real issue, and it really says you've got a problem. Your process is not centered. So let's take a look at the control chart now. We'll just take the normal curve, turn it sideways so you can get a good visualization. Control charts really do have those two purposes, as we said earlier. They act as a historical record, and they compare the results to the desired center of the process. So your X bar, the center of the process, really needs to, probably should be where you want that process to be. And again, you test to see if there's any evidence that the process is not centered. And your response rules, you can build whatever response rules you like. They need to be probability based. That's beyond the scope of today's discussion, but there's a lot of resources available to help you with control rules. It's really relatively simple, but they got to make sense to you. Control charts are really normal distributions, and it's important to bear in mind that normal distributions are only sensitive to the distribution of the values and not the values themselves. In other words, it doesn't matter if that value is a million, a billion, or 10, or 1. They're only they're only there to measure the variation around the mean. So we've constructed, in earlier lessons, we constructed a standard deviation. We plot that standard deviation on this new chart, and then we're going to kind of move forward here a little bit. So let's add range. Now, range is an important component when you're doing a continuous process where you have multiple samples and you may have a good deal of variation. All of our charts thus far have been discrete events, single events. Our slingshot was one shot at a time. And that works great if that characterizes your process. But in the mass process, if you're doing multi-item thermoforming, let's say you're making cookies or sheetrock or plywood, what have you, you're producing a lot at a time. So you want to take a lot of different samples. In continuous production, when you take those multiple samples, it helps ensure that you're not over or under reacting, because a single point may be misleading. But it does introduce testing error. So if your testing instruments are not calibrated, or they're highly variable, or your technicians who are doing the testing are not well trained, you certainly can have test error. So let's prepare to add the range. So you may want to decide, how many samples do I want? I would suggest you go 3 to 5 samples. During your normal operations, just gather that process, those samples, and begin to collect that data. Record all of the data, and then calculate the average range. We do have a spreadsheet for you. If you're interested, you can email me and get that spreadsheet, but it looks like this, essentially. So what we have here is we have our test numbers, and we've only used 6 test numbers, but you can do as many as you like. Bear in mind, you reach statistical significance around 35 samples, and your standard deviation will drop tremendously. The change in standard deviation above 35 samples will change dramatically. So what we do is we collect, in this case we're using 5 samples, so we have 5 individual measurements, and then we take the sample total, we get the sample average, and then we calculate the range. And the range is simply the maximum minus the minimum. Then we take all of these values, we calculate the total range, the maximum range, the minimum range, and then the number of tests. Then we calculate the average range, and we calculate the range control limit, which is the upper control limit for range. Obviously, if you have a 0 range, that's probably not a problem. So in order to calculate the range, we'll go to that in just a moment. We have this handy constant chart, and basically we have 5 samples. We're going to be using constant D4, which is 2.004, and our upper control limit range is D4 times R bar, which is your average range. So we'll take a look at that here. And we're going to plug in the average range. You can see that we've added the range chart down here. We've got our standard sample data up here, which does reflect the data in this chart. So what we're going to do is we're going to plot the data for each one of the samples, and we're going to plot it in both the range and then also in the X double bar. And when we populate it in the range, which when you read the control chart, that's the very first thing you want to look at. Because if you're above the upper control limit for range, which in our case is 170.88, then something is terribly wrong. Either there's a massive test error or your process is wildly out of control. Either way, you need to react to that. maybe shut the process down, get it recentered. So when you read the range, if it's above the average control limit, you've got a problem, need to react to it. If it's below the upper control limit, you basically just assume everything is in control and it's normal, plot the X bar, and read the X bar. So in this case, in test 1, we have a range of 100, which is slightly above the 80.8, but it is definitely below the lower control limit. We assume everything's fine. We plot that, and indeed, we're in the between the X double bar and -1 standard deviation. So in this case, everything is perfect. Assume you're in control and move on. So with that, I know this was fast. I know it was quicker than our others, but take a look at control charts. They're really an excellent tool if you're not using a closed loop control system. They provide that historical record of the process output, and the understanding and consistently applied action rules really improve the end product of consistency and thus your customer satisfaction. Be aware, control charts do not tell you where your process is centered. They only look for evidence that it's not centered where you want it to be. Okay? And control charts are a great tool when you apply them correctly. And truly, they are the basis for closed loop control systems. That's it for stage 3. I know this was fast. Feel free to replay the video. Very definitely, if you have questions, shoot me an email. Jerry@reefworks1.com is my email address. Feel free to send it to me, and if you'd like a copy of this spreadsheet, I'd be more than happy to give it to you. So in stage 4, we are going to cover closed loop control theory, and that's where it starts to really get fun and interesting. See you then.